everybody. Today we're going to learn how to calculate the average atomic mass for an element. Since elements often have multiple isotopes with slightly different masses, we can figure out what the weighted average is for them. So, elements have lots of isotopes. Some have one isotope, some might have two, some might have five. There's a big variety. I would never expect you to know which isotopes occur naturally. I would never expect you to know how many isotopes something has. I don't even know all that. That's the kind of stuff we would just look up if we needed it. But something I may ask you to do is if you're given the information about the isotopes, you should be able to calculate the weighted average. If I give you the atomic mass from the periodic table, you should be able to look at it and try to predict what you think the most common isotope might be. So we'll learn how to do that today. So what we want to do is we want to take an average that's going to account for the fact that not every isotope is as abundant. It's not as common necessarily. So if I were to take a big scoop of an element up, I would want to know kind of what the average mass would be. We are not going to be doing chemistry reactions with one atom at a time. I don't need to know what the specific isotope at a time is. We're going to be doing reactions with billions and billions and billions of atoms, right? So we need to have an average because we're going to see that average in our reactions. We have a whole bunch of atoms. We're going to have a variety of isotopes. So we need this average mass. So for carbon, for example, if you look at the periodic table, we find out that the weighted average is 12.011. That means if I were to take a big scoop of that element up, on average, it would have a mass of 12.011. One of the things we can do is we can look at the average and figure out what the most common isotope is probably going to be, using a little bit of common sense. So if carbon's average mass is 12.011, and I know that I have isotope carbon 12, carbon 13, and carbon 14, I can see which isotope this average mass is closest to, and that's going to give me a pretty good guess as to which one is the most common. Now, there could be some times where maybe you have a really close, maybe it's like a 50-50 or something, right? It may be a little bit more tricky, but this common isotope rounding problem, I would only give you if the answer was going to be pretty obvious. So whatever this rounds to, we'll go ahead and say is the most common isotope. So the next question is, how do we calculate this average? We're not just adding up these masses and dividing by 3. We don't do 12 plus 13 plus 14 divided by 3. Okay, that's a little too simple. That doesn't take into account that we have way more carbon 12 than we do 13 or 14. So what we're going to be doing is a weighted average. So I'll show you how to do that next. This equation looks a little awful at first, okay? But when you look at it piece by piece, you'll see that it's just repetitive. It may be long, but it's repetitive, okay? So what you're going to do is you're going to take the mass of isotope number 1, and you're going to multiply it by whatever the percent abundance is. So, if you have 80% of it, that's what goes here. Then you add to that the mass of isotope number 2 multiplied by its abundance. Then you add to that the mass of isotope 3 multiplied by isotope's 3 abundance. So if you only have 2 isotopes, you only do this twice. If you have 3, you do it 3 times. If you have 7, you do it 7 times. But you can see it's very repetitive. Mass times abundance plus mass times abundance plus mass times abundance over and over again. this is just a small tip that I've kind of gathered over doing this for the last however many years. I've noticed over the years that if you put your percentage in decimal form for your calculator work, we get fewer mistakes that way. You know, if you put in your percentage as an actual percent instead of saying like 30%, it's better to put in 0.30 because I just feel like people mess up more often. They forget the extra step of converting, back from the percent. So my suggestion is put in the 0.3 instead of the 30%. If it's 2%, put in 0.02, right? If you don't like doing that, you don't have to. It's just a tip based on what I see, the types of mistakes people making. All right, so here is an example. So let's say that I have these isotopes, 24, 25, 26. And let's say they tell me the actual mass. Now remember, this over here is the mass number. Mass numbers are always in whole rounded numbers because this is protons plus neutrons. But remember, they're not totally perfectly weigh 1. Like a proton and neutron don't perfectly weigh 1. We just do that to make our lives easier. And the electron technically is a teeny, teeny, tiny mass to contribute as well. So sometimes they may give you a more accurate mass. Okay? If they give you the accurate mass, use it. If they don't, then just use the mass number. Okay? Here are the percent abundances. So there's, about 78.99% of the magnesium out there is magnesium 24. 10% is magnesium 25. 11.01% is magnesium 26. So I'm going to convert the percentages into decimals. I find that easier. Because they gave me the real masses, I'm going to use the real mass. 23.99 times 0.7899 gives me this. 24.99 times 0.1. 25.99 times 0.1101. And now I add these all up and I get my final answer. Sometimes you're given the data like this in a chart, which is kind of nice. You can just kind of use the columns to make things easy for you. Sometimes it may be given to you like a word problem, and you may just write everything out more like an algebra problem. It doesn't really matter the format you use as long as you're showing your numbers and you're showing what you're doing with your numbers. You can't just go straight from the data to magically getting an answer, okay? So make sure that you're showing either the charts or, showing the equations that you're using. Okay. One thing that's a little bit trickier is that we can actually find the percent abundance by using a little bit of algebra. Okay. So we're going to use the exact same equation where it's mass times percent abundance plus mass times percent abundance, but because we don't know the abundance, we're just going to put in X. Now, for the second isotope, if we don't know that either, right, what we're going to put instead of a number is we're going to put 1 minus X. And people always say, okay, wait a second. I understand why I'm putting X for my unknown, but I have 2 unknowns here. And I don't understand why it's 1 minus this unknown. And what we have to remember is that the total adds up to 100%, right? And we usually, if we're using decimal form, right, 1 is the same as 100%. So, X is percent number 1. So if I subtract out, these would have to equal 100% when I'm all over, right? So if I just do 1 and then subtract out whatever this is, it will by default tell me what my other unknown is. So while it looks like I have 2 unknowns, because they're related to each other by this 100% concept, I can basically use that to my advantage to substitute and move things around so that I really only have one variable to solve for. Okay? So, let's calculate the percent abundance for a situation where we have two isotopes of boron. This was kind of nice. They gave me the actual masses. If they don't give you the actual masses, then just use the mass numbers. It's not perfect, but it's plenty good enough. Okay? So we know our equation is that the average weighted mass is mass number times abundance plus mass number times abundance. I was told what the average mass is. I'm told what the actual masses are. So now I'm just solving for the percentages. So let's plug that in. The average mass was given to me by the problem up here. Mass of isotope 1 was told to me from up here. I don't know what the percent of abundance is. Whoops. Getting ahead of myself. I don't know what the percent abundance is, so I'm just going to put an X. Isotope number 2, the mass was told to me up here. And I don't know what its abundance is either, but I know that it's going to be 100% minus whatever this was. So I'm just going to say 1 minus whatever this is. Now I can do some algebra, and I can solve for X. Be careful and show your work on your binder paper. I see people get all the way to this point. They try to do the algebra in their calculator, and they totally mess it up, and they get the wrong answers. Okay? So please, 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 please do the work on your binder paper. Okay? You have plenty of paper in your composition book for scratch work, for note-taking purposes. On worksheets, you have space on the worksheets to do it. Right? You can always staple on an extra piece of binder paper if you need to. Right? Show your actual algebra steps on paper so that you don't lose points for an algebra mistake. Okay? You got to make sure you're careful about that. So, if we solve for X, we find out that X is 0.1998. Let's put that back in percentage form by multiplying by 100. And I find out that the percent abundance of boron 10 is almost 20%. Okay? X was abundance 1. I solved for X. I found out what that abundance was. That's how common it is. Now, to get number 11, boron 11's abundance, I'm going to do the 1 minus X. That gets me my new percentage. Now sometimes people say, wait, but if I just plugged in my percentages, I wouldn't have to multiply down here. I know. I understand that. This looks like an extra step. All I can tell you is I see fewer mistakes this way. I see people doing crazy things where they multiply by 100 and like on accident at the end, and they start telling me that they have huge percentages. Okay? So I know it looks like an extra step to leave it in decimal form and then put it back into percentage. It's just statistically seems to be safer. Okay? So the other thing is I've noticed over the years that those problems seem a little bit overwhelming until we start to do some by hand. So kind of the second part of this lesson is going to be us doing worksheet number 12 together under the camera. Okay? So this video is going to end. We're going to switch to doing worksheet number 12. All right, hope that was helpful. Bye, everybody.